Good morning and good evening, everybody. Welcome to this webinar on digital tool for crash, turn competitor insight into cutting-edge crashworthiness. I have the pleasure to be here with Valentin Zaccardo, Product Manager, Digital Twin Solution, and Mark Gevers, Business Development Director in Tecosim, and Thilo Vollberg, Team Manager in Tecosim. Now I'm lost. Can I stop you 1 second? Yeah. To stop is? No, go ahead.
It's not recorded.
Yeah, sure. My name is Filippo Bona. I'm a Product Marketing Manager in E2MEC1. Sorry, I'm totally tight. Repeating what I was saying. Can we start again from the very beginning?
Of course.
Okay. Give me 2 seconds or 1 second. Okay. Fast.
Okay.
I have to go to the agenda. Or start back. Good morning and good evening, everybody. Welcome to this webinar, Digital Tool for Crash, Turn Competitor Insight into Cutting-Edge Crashworthiness. My name is Filippo Bona. I'm a Product Marketing Manager in E2MEC1, and I have the pleasure to be here with Valentin Zaccardo, Product Manager, Digital Solution, and Mark Gevers, Business Director, Business Development Director in Tecosim, and Thilo Vollberg, Team Manager in Tecosim. Let's go straight to our agenda. Let's go straight to our agenda. We will have first a short presentation, corporate presentation, and portfolio presentation made by Valentin and Mark. Then we will deep dive in Tesla Model Y. We will analyze the body Y tear down, and we'll give some information about the technology insight. Then we will have a performance insight with the CAE model, and we talk about digital twin for crash and NVH digital twin. Finally, we will have a 15 minutes Q&A session. I hand over directly to Valentin and Mark to present themselves first.
Thank you, Filippo. So my name is Valentin Zaccardo. I'm product manager in E2MEC1, working in this company since 3 years. I initially started with a background in mechanical engineering as product manager for Body in White. And also I'm taking over now all what we call the digital twin in E2MEC1, so the simulation, assessing the performance of vehicles thanks to simulation.
So I'm Mark from Tecosim. I'm in the CAE field since nearly 25 years and with Tecosim since more than 20 years, and I will give you an overview what you can do with the power of CAE in benchmarking. So let's start with E2MEC1 and Tecosim. And it was quite a surprise for me when we started. When we started the cooperation, I initiated the cooperation. It was a surprise to see that we are nearly the same size. So Tecosim is 600 employees worldwide.
E2MEC1 is about 730.
We have a global footprint. We have 300 customers. E2MEC1 has some more. But it was. Both are companies with nearly the same footprint, the same size.
Yes.
Within Tecosim, we are specialized on CAE, on simulations, and we are doing not only crash and NVH, so that's a part of the structural simulations. We are also doing durability, fatigue, whatever you can do with the finite element method. But we are also doing computer fluid dynamics, so you can see here a thermal simulation of a battery pack. We do multi-body systems, for example, vehicle dynamics. Next slide. We do electromagnetics, that's from e-machines to sensors and so on. We do system simulation, combining something, and we do process automation.
And on our side, so for A2 Mach 1, we are, as maybe a lot of you know, expert in benchmarking. And moreover in technology insights. So this is the core activity of A2 Mach 1 since 20 years, doing teardown, static benchmarking of cars. But now we are also grown up our activity since the recent year in the 8 most important automotive pillars, such as sustainability, providing life cycle analysis assessment of the car on the market, cost insight assessments as well, thanks to a full breakdown costing approach, market, supply chain, and software and IT services insight as well. And for the topic of today, with Digital Twin, we are assessing the performance, the dynamic behavior of vehicles, so multi-physics, but also we are doing it on physical tests, on energy management strategy to assess really the thermal efficiency of the latest BEV on the market. And what is very important is that all the data A2 Mach 1 is gathering among the current automotive world is uploaded in a accessible and user-friendly database. You just have to log in with your own account and you can save time, generate IDs also with very intuitive tools and 3D tools. You can also cost and assess the price of your competitor right from the platform. This is definitely your one-stop shop if you want to benchmark your competitor.
And on the basis of this, so A2 Mach 1 is doing scanning and material analysis and scans also the connections. That is all the input you need to build simulation models to deeply understand your competitor. And you cannot do it only for crash and NVH. You can do pedestrian protection with it. You can do electromagnetic conformity with it. You can do, A2 Mach 1 is also delivering aerodynamics on top of this data. You can really analyze your competitor instead of measuring it.
And this all from the comfort of your computer, because you don't need anymore to rent or do expensive physical testing. So that's really also a cost and CO2 effective solution than doing virtual benchmarking.
Please look at the camera at the maximum. Don't too much look at your eye, both of you, because you can do it sometime, but not all the time. You really
Okay.
need to focus on the camera.
Focus on the camera.
Okay.
Thank you. Thank for the hint.
Okay.
Yeah. So sometimes when he's telling something, I will step on. Yeah.
Yeah,
Okay.
okay.
Yeah. Okay. Understand.
So let's now jump into the Tesla Model Y, which is the topic of this today webinar. Let's deep dive in the technology insight of this car. So in A2 Mach 1, since years, we are dismantling cars, analyzing all their components, rebuilding their digital mock-up in a 3D environment. And by doing so at a certain step, we stop to the body in white. And on this vehicle, which is also the most sold vehicle, BEV vehicle in the world today, we have discovered very never seen solutions. As you can see on the body in white, there is no floor, there is no cross reinforcement, there is no seat attachment points. And you can immediately identify those 2 giga-casted units that we have brought here on our set today for the front and the rear unit. Okay. To be honest, at a certain step during the dismantling, we knew that this vehicle was very special due to the fact that it's one of the first cell-to-body application on the market. The battery is very structurally part of the body. It's a never-seen solution. So we wanted to investigate what is the acoustic and contribution of the battery to the global stiffness of the car. And by doing so we have done the very known Hammers test. So we equip the body in white with 20 sensors to measure the local acceleration when we excite the car body with a hammer, basically, thus identifying the modal shape and their corresponding eigenvalue, their frequencies. And we have done this operation in 2 times, with and without the battery, also with the chassis subframe, all the structural components still assembled, to really gather some input and understand the battery contribution to stiffness. Then the dismantle was proceeded, and at a certain stage, so we kept the body in white, and what we do, here I will explain you our body in white process, we cut it on the y-axis. And the process I explain here is really a global process. So we are delivering technology insights for body in white, for European vehicles, North American vehicles, and I'm glad also to announce you that starting of next year, we will do Chinese and Indian vehicles. So the process I will explain here is really standard and done on a global level. We cut the body in white, we process the driver side always, so the right side on the left-hand drive market, right-hand drive market. And the aim is really to gather the bill of material, so to isolate every component of the car body. The aim is to identify all the cost drivers, the part weight, the type of material, the process, and we collect also all the connections. We report it into our platform. And for instance, for this gigacasted part, I will show you the demo, this physical part, and the associated information into the platform. This is the A2 Mach 1 platform. So today we have 347 vehicles covered by the Body in White program, many vehicles on different markets. You access it very easily and you have an immediate view on all the sub-assemblies of the vehicle. You can download the bill of material as an Excel file. And jumping into this very special part, you have the information about the weight, number of fasteners, so the cost driver. You have the reporting of every connections with the different part of the car body. Standard view of picture, front, left, back. And also for all the connections, all the eventual weld spot or welding line, we are reporting them also visually into the platform. And we are not only reporting it, but also monitoring them thanks to an assembly tree. So basically it's a big tree with leaves and branch. So every tree of the leaf is a single part and every branch is a sub-assembly. So you can really accurately monitor every connections between all parts and benchmark against market peers the body assembly strategies. This is not only what we do. On top, we also do scanning. This is a process we have introduced last year. It is optical scanning, and here again, let's do an example in the A2 Mach 1 platform, in the 3D Explorer. We will cross-compare 2 cars, 2 EV, the Tesla Model Y with the Giga casting solution, and the more conventional metal sheet assembly design. You can see on the same screen, we are cross-comparing with the same coloring every part. We can isolate, for instance, the body structure only, and why not isolate the front unit to see at the same perimeter what are the number of parts between 2 vehicles. And this is a very good example, actually. You can see on the right the Tesla Model Y, on the left the Renault Megane E-Tech. And you can count, you can really explode the view to understand the assembly strategies of your competitor. And last but not least, for every part of the vehicle, we also do material analysis. And for this Tesla Model Y, we have been a bit deeper than our usual process, because we wanted to assess what is the ultimate tensile strength of this part. In case of main crashes, for instance, this is a very good mechanical KPI. So we have cut dedicated coupon samples, machined them, and performed a tensile strength testing. But also on our standard process, what we do, I will show you on the platform right now. If we take, for instance, an external part, an auto skin, this is the body side. We always do surface hardness testing, core hardness testing. So you have this information reported in a database. Also the chemical composition. This is a very valuable data for raw material providers. And we assess, we measure, thanks to microscope analysis, the different layer of coatings, for instance. And again, what is very important is that every analysis that A2MAC1 is doing is done on a standard basis. So you can cross-compare this data among all other vehicles we have benchmarked up to date and on every market in the platform. Another interesting insight on this vehicle. As you can see, the inner structure of the body side is a Taylor welded plank. And even here, so we do not measure the core harness only on one plank. We do the 5 planks, so to identify the different grade of steels. And we measure the different thicknesses, because this is also a Taylor welded plank, one stamp, but many grade of steel, many thicknesses on the same part. So every information, all the technology insights about your own body in white or the one of your competitor is really uploaded in a standard basis in the platform. So just to summarize, we cut the body in white, and we dismantle, we do 3D scanning, material analysis, and on the passenger side, we do not keep it alone. We do also cut cross-section. We reference in the database to identify the addition of external features and functionalities. And we do this also on the main cross-section that contributes to the load path of the body in crash event. So this is also stored in the database. Thank you. And now, speaking about cross-section and energy load path, what about?
Yeah, let's continue. Valentin already mentioned that we have done NVH tests on this vehicle, where we have both parts in. We have done, of course, then a CAE model based on the 3D data, the material data, the connection data. We build up a body model, and then we do a correlation of this body NVH model against the NVH tests. And we have done it with the battery connected, and give me it's better, I think. And we have done the same without the battery connected. And we found the first surprise. The first surprise was that the frequency of the torsional mode, that's the main mode of the body, the frequency is the same with and without the battery. And I was wondering, I'm a crash guy, I'm not so deep in the NVH area, but a colleague of mine explained it to me, and there is a reason behind it. And with the model, with the help of the model, you can answer this question: why did they do that? The digital twin, in this case, for NVH, can give the answer. And the digital twin for crash can give other answers. And with this statement, I will hand over to Thilo, my colleague, and Thilo will show us crash results of this very special vehicle.
Hello, I'm Thilo Fröberg. I'm with TECOSIM for 13 years, and I'm a team lead in occupant, pedestrian, and every kind of safety which is human regarded. So what we see here is basically the crash model, which was derived out of the data which has been shown by Valentin. So after the scanning process, we basically get a set of data which we then convert into a CE model. So right now, this is, for example, a side crash pole. I will just play it for you. So this is a normal crash load case, which is performed to bring the car to the street. Sorry. And basically, what we can do now with this simulation, we can not only look from the outside, we can look from the inside. So, for example, I can now look into the area of the impact. And we can investigate if, for example, the battery casing is touching the battery cells. As you can see here, the sill area and all the structure prevents a contact between the battery cell and the casing. We can further look into numbers. For example, here we can see a curve of the intrusion of the battery casing into the cells. So you can see basically how much intrusion we have, and if we have a contact. For your explanation, the bottom left corner would be 0, so you can see there is residual space. Furthermore, we could investigate how the battery casing is moving in relative proportion to the body. So for example, here you can see it is breaking away. We can then also look at force levels of screw connections, or look at bolts, look at weld lines, welds, and see if they fail, if they are stable, and we can analyze the structural behavior of the car.
So that's the topic. It is analyzing instead of measuring. That's really important. You can analyze your competitor as deep as you analyze your own product with your own simulation models. That's the same approach. No one is doing the development with prototypes anymore. There are less prototypes. There are prototypes, but less. And everything is done on simulation base. And in the benchmarking, we give you the same power.
So to perform all of this, a certain set of tasks has to be performed. So let's have a look at the model. So here you can see the simulation model of the Tesla Model Y. It contains roughly 11 million elements and is divided and built up like a normal OEM model would be. This means, first of all, the car is divided into several packages, like the body in white, which contains the castings, as you can see, and the structural parts of the body. Then part of this body in white is the battery casing. And of course, we have all the closures and bolt-on parts available. Everything is connected state-of-the-art for the automotive industry. And to create a model which we can analyze in crash, there has to be a certain quality attached to it. So let's have a deep dive into the quality. So here we can basically see our mesh quality up close. So to let you know, after the scanning process, we have a randomized set of points in the cloud. This will not represent any CAD data. So there is a specialized process which we perform to regenerate real mesh data based on representing a CAD-based quality, let's say it like this. So this means our data is not only looking good and every edge is defined. On top of that, our data is penetration-free. What does this mean? Let's zoom into this area, for example. Here we can see the flange area, where the outer and inner sheet metals are matching. And in between, we can see the spot welds. As you can see, all the data is perfectly aligned. We have no intersections and no penetrations. And this needs to be like that, because otherwise we will not be able to perform the crash analysis and to connect everything properly. Coming to the connections. So this model consists of a lot of connections, and all of those are manageable, also by yourself. So we have nearly 3,000 connections in this vehicle, and from these connections, 2,000 are spot welds. We can see them here. This is every spot weld that has been registered in the A2 Mac 1 disassembly process. Each of the spot welds is assured to be perfectly located and to have every connection partner as it was recorded. On top of this, we have seam welds, we have screws, rivets, and adhesives. All of this is in an ANSA connection file, which means you can manipulate it, you can change it, you can even exchange the description with your standards. So, going to the next stage. Valentin was talking about materials. Let me get everything back on. So, let's have a look at the materials. We have attached a large material library, completely open for you. Everything is accessible, which is divided into main regions like materials for bushings. Also bushings are defined in the chassis. And we have steel materials, which are called ST, aluminium materials, AL, and plastics. So let's have a look at the steels. Steels are divided into different grades, like dual phase, hot rolled steel, boron, or normal steel, cold rolled. So let's look into one of those materials. Our material cards are not just linear elastic material cards. They contain failure and they contain strain rate dependent data as well. So as again, state of the art for crash development. All the materials which have been recorded from core hardness testing from A to Mag 1 have then been reapplied here in the model. So for example, if we look into some of the high-grade materials here, let's take some of the dual-phase steels, and maybe let's take the boron. We can see areas where high-grade steels have been applied. Yeah. Also, Valentin was talking about one specific part I would like to show you. So inside of the B-pillar, we know there is a Taylor welded blank. And this also has been replicated inside of our models. So we take care that all the necessary